So far, we saw that each baby's mother has a random smoker, non-smoker label in the column shuffled label, while her original labels is in maternal smoker. If the null hypothesis is true, then all the random rearrangements of the labels should be equally likely. Let's see how different the average weights are in the two randomly labeled groups. When you run the line of code down here, you're basically looking at the result of the shuffled label and the birth weight average. Basically, the group labeled as false, non-smoker has an average weight of 119.28. And the group labeled as true has an average birth weight of 119.75. So basically, these two averages are very close to each other, reflecting what you would expect under the null hypothesis. If maternal smoking had no real effect on birth weight, any random grouping should produce similar average birth weights. The averages of the two randomly selected groups are quite a bit closer than the average of the two original groups. We can use our function difference underscore means to find the two differences. Well, let's take a look at our result of the function. We pass in two arguments, original and shuffled, along with shuffled label. The result is going to be 0.47. Now, if you take a look at the difference of means between original and shuffled and maternal smoker, you're going to see you have a negative number. This negative number basically is saying that, hey, on average, babies born to smoking mothers weigh about 9.27 ounces less than babies born to non-smoking mothers. Now remember that a small difference here showing and is consistent with the null hypothesis. Very good. But could a different shuffle have resulted in a larger difference between the group averages? To get a sense of variability, we must simulate the difference many times. As always, we will start by defining a function that simulates one value of the test statistic under the null hypothesis. This is just a matter of collecting the code that we wrote in the previous slide. So the function one simulated difference of means, it takes no argument, and it basically returns the difference between the means birth weights of two groups formed by randomly shuffling all labels. There's a breakdown of the code of the function, and basically we can take a look at the result by passing births, birth weights, and maternal smokers. The number that you're going to see is negative 0.058, 2994, and the rest of the digits. This output indicates that in this particular random simulation, the average birth rate of the shuffled non-smokers was about 0.0583, less than that of shuffled smokers. Because the labels are shuffled, this difference doesn't imply any real relationship. It's simply a byproduct of random assignment. So on the next step, we need the permutation test. Tests based on random permutations of the data are called permutation tests. We are performing one in this example. In the cell below, we will simulate our test statistic, the difference between the average birth weight of the two randomly formed groups many times and collect the difference in an array. This process is repeated 5,000 times in this case to create a distribution of the test statistic under the null hypothesis. Each time, the difference in means between the shuffled groups is calculated and stored in differences array. So now if we'll take a look at the next line of code, basically, we try to visualize the result of the permutation test by creating a histogram of simulated difference between group means and overlaying key information like the observed difference. The observed difference is going to be negative 9.2661, which basically is the actual difference in birth weights between the smoker and non-smoker groups in your original data. The difference is far from zero, indicating that the true difference is much larger than what you expected under the null hypothesis. So take a look at your histogram. Notice how the distribution is centered roughly around zero. This makes sense because under the null hypothesis, the two groups should have roughly the same average. Therefore, the difference between the group averages should be around zero. The observed difference in the original sample is about negative 9.27, which doesn't even appear on the horizontal scale of the horizontal line for your histogram. The observed value of the statistic and the predicted behavior of the statistic under the null hypothesis are inconsistent. So, the conclusion of the test is that the data favor the alternative hypothesis. It supports the hypothesis that the average birth weight of babies born to mothers who smoke is less than the average birth weight of babies born to non-smokers. If you want to compute an empirical p-value to have a better result, more consistent result, remember that low values of statistic favor the alternative hypothesis. So if we calculate the p-value in this case is basically very, very small. We are checking the proportion of 5,000 simulated differences that are less than or equal to the observed difference, which is approximately negative 9.27. For the empirical p-value, the empirical p-value is a number between 0 to 1. In this case is 0.0. A small p-value, which is basically less than 5%, indicates that the observed difference is unlikely to occur if the null hypothesis is true. So when p-value is less than alpha, we reject the null hypothesis and support the alternative hypothesis. The empirical p-value is 0, meaning that the none of 5,000 permutated samples resulted in a difference of negative 9.27 or lower. This is only an approximation. The exact chance of getting a difference in the range is not 0, but it's vanishingly small. So according to our simulation, and therefore we can reject the null hypothesis. That's the conclusion based on the p-value that we calculated. The p-value is very small. Since p-value is less than or equals to alpha, you're going to reject the null hypothesis. And you're going to support the alternative hypothesis that there should be a difference between the weight of newborns.